Hello and welcome back. Let's continue with our lecture on general theory of relativity. So far we have seen various aspects of curvilinear geometry which are general in nature. We have encountered a problem that the partial differential in the flat space time where all the laws of physics are expressed are not covariant. That is, they don't transform like a tensor from one coordinate system to another coordinate system. Now we have defined new covariant derivative, that is, which transform as a tensor from one coordinate system to another coordinate system with the help of connection which are not tensors themselves. So this connection is a very general property. So you can define your own connection and have your own differential operator which can be transformed as a tensor. Now this very general nature is fine from mathematical aspect, but physics we are mainly concerned about the mathematical structure which is closely bound to the geometry, and that is where the Riemann geometry comes into picture. Riemann geometry is a special geometry in which you have a special connection which is called the Christoffel symbol. That is what we are going to look into this lecture. Once we have a Riemann geometry, this closely connects the geometric aspects such as a covariant derivative, connection, and metric tensor in all single entity, and they are closely connected with each other. It's quite useful to have this Riemann geometry because it leads to concept of what is called locally Euclidean or locally Minkowskian coordinate system, where it is a coordinate system in which the connections are zero and leading to partial differentiation as a tensor quantity in that specific coordinate system, where you can apply your simple laws of physics, then generalize them to arbitrary coordinate system. Let's continue with the lecture. This is a part of course PH4205 at IISER Calcutta. Let's continue with the lecture. First concrete step we have taken forward from the flat spacetime to curved spacetime is the covariant derivative of a vector field, which is defined as the covariant derivative of a covariant vector field is given as del alpha t beta is equal to dt beta by dx alpha minus gamma sigma alpha beta t sigma, and covariant derivative of a contravariant vector which differs only by the sign by which it is added here. We have seen that the sign difference is such that the dot product between a covariant and contravariant vector lead to a scalar, and effectively the differentiation turns out to be partial differentiation. The connection is basically a transformation of tensor or vector field from a given point to another point, such that the vector operation on a tensor at two different points can be done in order to define the covariant derivative. Now we can extend this covariant differentiation to any higher rank tensor. The idea here is simple, that each covariant component or contravariant component need to incorporate gamma. Whenever there is a covariant index involved, there comes gamma with the minus sign, and whenever there is a contravariant index involved, then the gamma comes with the positive term. So when you have a second rank tensor, the first term naturally should be partial differential, because in case of flat spacetime or inertial system where gammas are zero, this operation should go back to the partial differentiation. So then each of the tensor indices, in order to cancel the non-tensorial term, we need to have a gamma term, and that is why we have a 2 gamma term for second rank covariant tensor. Same way we can have a contravariant vector. First term is a partial differentiation, then gamma comes with the positive sign here. We can also have a mixed rank tensor. In this case, again, first term is the partial differentiation, then there will be 2 terms corresponding to gamma because of the second rank tensor. First would be corresponding to the contravariant tensor, which would add gamma term with the positive sign, and second would be covariant term which comes with the negative sign with the gamma. So this we can extend to arbitrary rank tensor. Each rank will acquire one gamma positive or negative sign based on it is covariant or contravariant tensor. Now again, fundamental question is about the connection. What would be the constraint? Now so far we have seen connection is just a way of transporting a vector from one point to another point. Now in order it to connect very closely with the geometry, we somehow need to connect it with the metric tensor. So can we relate gamma to metric by some means, or make an extra constraint on gamma such that metric is involved in some way? The answer is yes. Now one of the idea is to say that your metric tensor is constant with respect to new derivative operator or covariant derivative operator, that is delta sigma G alpha beta is equal to delta sigma G alpha beta upper is equal to 0. What is the reason for that? We have seen that in the Minkowski space or the flat space time, we have a metric which are constant. That is, their partial derivative with respect to space time coordinate is 0. If we simply generalize this idea to the curved space time, now we have a new differential operator, that is covariant differentiation. Intuitively, that our metric also should remain constant with respect to this new covariant differentiation, and that is reason to impose this condition or covariant differentiation of both upper and lower metric is 0. One of the other reason to use this constraint is that some simplification happens when we do some of the algebraic calculation. For example, let us look at covariant differentiation of a covariant tensor. Now, we would like to raise and rover. We know that any covariant vector can be transformed to contravariant vector and vice versa using metric tensor. Now, suppose this covariant vector T alpha, I want to express in terms of the contravariant vector. So that means it has to involve a GAB. T alpha is equal to G alpha beta T beta. So this is the expression where GAB comes inside the bracket. Now if we use the product rule of differentiation, the first I will have the GAB into differentiation of the tensor, and second one I will have the T beta, and then I have a differentiation of metric tensor. Now we say that this term is 0, and then we end up having a result that G alpha beta into delta rho T beta. So this is equivalent to saying that I can raise and lower the indices outside the differentiation or inside the differentiation, because metric itself is a constant. This reduces lot of algebraic operation. You see that the metric is constant, lead to a lot of simplification in the equation. This is also one of the motivation for using this constraint, that hence defined your covariant vector should see metric tensor as constant, or in other word, derivative of a metric with covariant derivative of metric tensor should be 0. Now this is what essentially leads to Riemann geometry. Riemann came up with the following interesting suggestion that use two additional identities, that is one, the derivative of covariant vector with respect to metric is 0, and second is connection should be symmetric. If you assume these two conditions, then the geometry is called the Riemann geometry. The Riemann geometry is based on these two assumptions. This basically ties the metric tensor to the geometry, and it makes an integral part of the differentiation, and connection is defined with respect to the metric. One can have explicit relation between the metric tensor and the connection. So this is essentially what we call the Riemann geometry. Now onwards, we will focusing only on the Riemann geometry. We will see that later Einstein used the Riemann geometry based on some of these property, and that is where the Riemann geometry is used in the theory of gravity. Once it is clear that what are the conditions to be used for the Riemann geometry, we can go ahead and use this constraint to define the connection in terms of metric tensor. We start with covariant derivative of a metric is 0. So let us explicitly write down it is a second rank covariant tensor. So it should have three terms. The first one is a partial differentiation with respect to the coordinate. Then we have two terms involving the gamma. So here is the equation explicitly. Delta rho G alpha beta is equal to partial differentiation of G alpha beta with respect to X rho. And then we have a gamma sigma rho alpha into G sigma beta minus gamma sigma rho beta G alpha sigma is equal to 0. Now we can use explicitly that the symmetry of a lower two indices of a connection coefficient. The way to use it is that we use something called the cyclic permutation of these indices. So these indices are only namesake because this identity is valid irrespective of what you call these indices. So we cyclically change rho to alpha and alpha to beta and beta to rho. So this way we can obtain two more equations. Let's look at the first equation. In this equation, all the rows are converted to alpha. That is, this one row is converted to alpha. This row is converted to alpha. This row is converted to alpha. And last term, which involves row, is also converted to alpha. Same way you can look at this. All the alpha in the first equation is converted to beta in the second equation, and all the betas are converted to rho in the second equation, and hence we obtain the second equation, which is in principle same as the first equation, except that symbolically it is a rewritten. Now we can again do this because there is a cyclic permutation. We can write down 3 cyclic permutation. The third equation again, it does same thing. Alpha goes to beta here, and then beta goes to rho, the beta goes to rho, and then rho goes to alpha. We do the same thing to converted equation, or if you want to do it from the first equation, then rho goes to beta, alpha goes to rho, and beta goes to alpha, both ways. But it is easier to start from the second equation and apply the same rule again, and then you would get the last equation. The reason for doing this is that the symmetry of gammas can be now simply be applied here. You see that we have various combinations here, but some of the terms have upper indices remain same because that does not take part in the cyclic permutation because it is a dummy index that does not play a role in our cyclic permutation, and hence that doesn't change. So all other combination we have taken, so we would get the combination of a lower one, which is a flip once. We are going to combine the term and rewrite. Let us look at the terms which are equal due to the symmetry properties of gamma. The first here marked in the red triangle is same as this. You can see that sigma is a dummy index. It doesn't matter. Then you have rho beta and then beta rho. From our assumption, these two are same now. Then we have sigma alpha and alpha sigma. Metric is symmetric. We have always used the metric tensor to be symmetric in indices. So these two terms are same. Then let's go ahead and see that one marked in the blue are also same. Again, the top index doesn't matter. Lower first two index of gamma are alpha and beta, and this equation, it is beta and gamma. They are same because of the symmetry property. Then metric also comes with the flip term, and we can again use the symmetry property of a metric, and these two terms again becomes same. Now look at the last term, and that is which is marked in green here. Again, this is a dummy index here, then rho alpha and alpha rho, that is the same because of the symmetry property, and then beta rho and rho beta are also same. Now we see that all the terms have some of the common combination, and let's name them 1, 2 and 3. Now we can get rid of a lot of these terms by simply using the combination that add equation 1 and 2 and subtract the third one. Because of the symmetry property, we cancel out these two terms because they are same, and then we also cancel out these two terms, and what is remaining is these two terms, which we can simply say that it is a twice gamma sigma rho alpha into g sigma beta, and then what is remaining is we have all this partial differentiation here, which we can write in this term. So first one is a differentiation of g alpha beta with respect to x rho, and then second one is differentiation of g beta rho with respect to x alpha, and the third one is subtracted because there is a minus here. So we have differentiation of g rho alpha with respect to x beta. So this is a simplification we get by assuming gammas are symmetric, lower two indices, and using the property that the metric tensor itself is symmetric, we get a simplified expression. Let us go ahead and simplify this. Further, we can get the connection between the metric and the connection coefficient. So all we have to do is multiply by G beta delta here. We have done these tricks earlier. Now we multiply this on both right and left side. On the right side there is no simplification. On the left side we get the Kronecker delta, and we can simply rewrite the equation as gamma delta rho alpha is equal to half G upper delta beta into this differentiation of metric tensor, that is partial differentiation of a G alpha beta with respect to x rho, and second term is differentiation of G beta rho by x alpha subtracted by partial differentiation of G rho alpha with respect to x beta. So this is essentially is relation between the connection and the metric tensor in the Riemann geometry, and this specific connection is called the Christoffel symbol. First thing, or the trivial thing to notice here, is that if the metric is constant or the partial differentiation of metric is 0 with respect to the coordinate variable, then you have gamma is equal to 0 and partial differentiation becomes the covariant differentiation. This is essentially going back to the Minkowski space-time from the general Riemann geometry. So this approximation is very important because we should be able to get back the special theory of relativity in absence of curvature, and that is what essentially possible in the case of Riemann geometry. Other geometries it may not be possible. So we will see that little later or in the coming lecture. We have complete description of a Riemann geometry. Now we have expression for the connection in terms of the partial differentiation of a metric tensor, and this specific connection in the Riemann geometry is called the Christoffel symbols, and they are called a symbol because they are not tensor. We have seen this. It is important that they are not tensor so that they are able to compensate the term coming because of the partial differentiation. Riemannian geometry, in which all the covariant differentiation can be completely written in terms of the metric tensor and its derivative. Okay, let us go ahead and let's take an example. In this example, we compute the Christoffel symbol for the Riemannian geometry described by the metric tensor ds square is equal to d theta square plus sine square d theta. This is a standard line element on a sphere. So with this we have already calculated the connections in this geometry using somewhat non-standard method. That is, we have identified the equation of motion with the geodesic equation of motion where the gammas come explicitly, and then we have compared these two equations and obtained the gammas. However, that is not the standard way of doing. The standard way of doing is basically using the expression what we have now derived in terms of the derivative of the metric tensor. Now we need the metric tensor and its inverse tensor. The metric tensor is basically diagonal. That is, diagonal components are 1 and sine square theta. We can easily invert this metric because it's simply diagonal, and all the diagonal element becomes inverse, and then upper indices of metric tensor GAB is given as 1 and 1 by sine square theta. Again, when theta becomes 0, there is a coordinate singularity here. Again, I am using indices. We are using Latin for 1 and 2. Only in 4 dimension we use Greek indices. Now we have a relation for the gammas. Let's evaluate first gamma 1 or gamma theta AB, where AB is 1 and 2. So we simply write down this expression, and only term which comes here is this one. This is the same as this, and P is a summed over, that is 1 and 2. But we see that because of the diagonal nature of the metric, the P can take only the value of 1. When P takes the value of 2, this metric is 0. So in principle, we can write it as a G11 and then G1C differentiated with respect to XB, G1B differentiated with respect to XC minus GBC differentiated with respect to x1. Now we see that again several simplification happens. We have to keep an eye on the metric coefficient. Cross terms would not exist. Let us find out gamma 1, 1c. So this is 1c. So this we have already written. B we fix to 1. Then we see that G1c, it is differentiated with respect to theta, and this is a general. G11 differentiated with respect to xc, and then G1c differentiated with respect to theta. So now we see that this term is unimportant because G11 is constant. Okay, so this is a G11. So it is constant. So then we can further simplify this. We get only two terms. And now we can fix the C. We can fix C to be 1 because otherwise metric component doesn't depend on phi. So this is the only one which resulting in, and that looks like it is equal to 0 to me. Now we can compute gamma 1, 1, 2. Again we can substitute 2 for the C. And then we see that now the first term is G12, which is 0, and the second term is also G12, that is 0, because we don't have cross term in the metric, and that turned out to be 0. We can compute G12C. Again, we have put B to 2 here, and then you have this term, which is going to be 0, because metric doesn't depending on phi, and then we have the second term is also 0, because we don't have a cross term in the metric, and we left with only one term, that is differentiation of G2C with respect to x1 or theta. So we have gamma 1 to 1, that is the only possibility, that is equal to half G11 minus G21 differentiated with respect to theta or x1, that is 0. And then let's do the second one, that is gamma 1 to 2, that is again takes the form of half G11 minus G22 differentiated with respect to theta. This will go through because we have sine square theta there. We have to differentiate that, and then we would simply get this expression gamma 1 to 2 is equal to minus sine theta cos theta. So you see that a lot of calculation involved, mainly because of these summation over the dummy indices. We have a lot of summation here, and that is why the earlier calculation which we have done looks rather simple, because it involves computing the Lagrange equation of motion, which all physicists are really experts in doing, instead of this summing over all the dummy indices, looking so many terms and so on. Now we can use the symmetry property to estimate some of the terms. So these are the trivial stuffs which involved in the calculation of. We have a lot more component to go. So that is we have done gamma 1 BC. Now we have to do gamma 2 BC. Now this also expression takes the following form. You fix 2 here for the metric component. Then since it is a diagonal, only value which comes is G22. Then you have the rest of the expression. Following the same line as we have done, we can get rid of the term whenever they don't contribute. Last term here is basically differentiation with respect to phi. We know that the metric doesn't depend on the phi, so that goes away, remaining the two terms. First we calculate gamma 21c, take the form G22, differentiation of 2c with respect to x1 and differentiation of 21 with respect to xc. So this is going to be 0 because we don't have a cross term. Okay, then we can explicitly put c to 1, then what we left with gamma 2 1 1, and that turns out to be 0 because this cross term comes in here. Now we can compute other term, that is gamma 2 1 2, that turns out to be half G22 upper and differentiation of G22 with respect to x1, which is non-zero. So we have to compute that, and that turns out to be half sine square 1 by sine square theta into 2 sine theta cos theta. So that leaves gamma 2 1 2 is equal to cot theta. From the symmetry argument, we also have gamma 2 1 2 is cos theta, and non-zero gamma terms for the sphere are the gamma 1 AB. There are 4 terms there, 0 0 0, and last remaining term is a minus sine theta cos theta, and the G2AB is a 0 cot theta 0. So you see that this is the same result which we have obtained earlier using the Lagrange equation of motion. Here we are explicitly computing the gammas and we are getting the same result, except the calculations are little lengthy. We have no way to figure out which are 0 and which are non-zero a priori, which does not happen in the Lagrangian. We can simply identify the 0 term looking at the equation of motion. Let us count the Christoffel symbols. How many are there? In n-dimensional Riemann space, we have a gamma. It has 3 indices, that with no symmetry, it should have a totally n into n. terms, that is n cube terms. But we also have a symmetry in the lower indices. That means that the last two n square terms have to be replaced by n into n plus 1 by 2. So we basically totally have n into n plus 1 by 2 terms in the Christoffel symbol. The rest of the terms are depend on each other. So there is a homework problem which is to derive the expression for the gamma in the Riemannian geometry in terms of the derivative of the metric. That is basically derivation which I have done here. You need to rewrite and submit it. And then you also have a exercise for computing the Christoffel symbol for the Riemannian geometry given by the metric ds square is equal to d chi square plus sine hyperbolic square chi d phi square. Now this is again two-dimensional space. You are supposed to do this using the both Lagrange equation of motion and explicitly using the expression for gamma in terms of the derivatives of metric tensor, and then upload your answer on VLearn. Let me stop here and continue with the next lecture.